Okay, so we talked about the random variable x, which was the number of passengers. Then we talked about the random variable c, which was the cost per passenger. Now we're looking at the random variable v, which is the profit, right? So this is what we charge subtracted by our cost to see what we actually make. So here we were told that v is equal to the cost minus $100. Now, assuming you have C correct, you can fill this out. But another representation is that we know C was $150 per customer, so that $150 per customer minus the $100 fee will tell us the profit per each of these group sizes. So again, here's what I can do. It's quick mental math, right? 2 times 150 is 300, 300 minus 200, 100 is 200, etc. You can just take your values of C and subtract off the 100 from each of those. So this was just from the random variable we had above. In the calculator, that looks like the following. Stat, edit, and in L4, we're going to go here. Well, we know you can do one of two things. You can do L3 minus 100, or you can type in this function here that we've modeled. So I'm just going to take the cost per group size, and I'm going to subtract off the 100. And then voila, we get our values here. So in order to find their statistics, we go to stat, calc, one variable, and sorry, I keep saying statistics, but it really should be the parameters, since these are the parameters for the random variable distribution here. So we're looking at L4, and of course it's parameters because I'm using mu and sigma x because I assume this is our population in the long run. So the list I'm looking at for the x values is L4, and their relative frequencies is L2, their probabilities. So we get the following. Okay, so now again I'm going to model this out. The mu, this mean expectation of v, is equal to the sum of its outcomes times their probabilities. And the sigma of v is also equal to the sum of the products of the differences here. So we do this 200 times 0.15 plus dot dot dot, the ellipse, all the way up to 800 times 0.05, which from our calculator output gave us $462.50. Box that up. And then our standard deviations, again, 200 minus the mu here of 562.50 squared times its probability, 0.15 plus dot 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 plus. I'm just going to leave that there. This is equal to 163.46 again. So we can see that multiplication alone would change the spread here. And it did from the original. If we look at this 150, and our original sigma was 1.09. So let's see what happens when I take 150 times 1.09. Look at that, I end up with 163.5, and here I have 163.46, pretty close if we round to the tenths place. And what if I took my original mean? Our original mean for the distribution was 3.75, so if I take 150 times 3.75, 562.50. It's almost like there's a pattern here. Okay, so what if I took our original mean, and then I subtract off 100, and I get 462.50, okay, and then remember, addition and subtraction don't change the spread, so that's still the same thing as the 150 times the standard deviation, so that's not going to change. So we actually discovered here that we have a few rules. It is important to be able to compute these by hand, but I'm not a mathematician of madness. There's always a method behind our madness, so we actually have a few properties here that we're able to follow. Very similar. If we are adding a constant, we know that that changes centers, but it does not change spread. So that means the mu of y here would be equal to this constant plus the original mean. However, if we look at the spread of y, we are not changing the spread really. If we're just adding, we're just taking the thing and we're moving it over. Kind of like SpongeBob when they're like, what if we take Bikini Bottom and push it over there? Well, that's all we're doing here with our spread. We're just moving the actual distribution. We're just moving it over either to the right or to the left. so it's not going to change our spread here. And so if I want the standard deviation of y, I'm going to take the absolute value here of the standard deviation of x. Okay, so that's what happens with addition or subtraction. Now, with multiplication for a constant, we know that if we multiply, it changes everything. So that's going to take b times the original average. To find the variance, we're actually going to do b squared. Oh, sorry, I want the square on the outside, not on the inside. I'm going to square everything, PEMDAS. Going to take that constant, square it, and then, why can I not write? This is why I need to finish my green tea before making these videos. So our new variance is equal to that constant squared. And then if I wanted the standard deviation, since I'm taking the square roots, again, I'm going to take the absolute value of b times the absolute value of the sigma. Okay, and then lastly, as we saw for this addition and multiplication, that'll change the center. So we're going to add this change to the mean. For the for the variance, same property will follow. We're going to square the constant we're multiplying. Addition and subtraction do not change spread. So we're going to ignore that a. We're just looking at the b here. So that'll give us this here. And then, of course, you'll notice that these two are relatively similar because we just care about the multiplication. The addition of a constant will not change the spread here. And I put x instead of y. I was just so excited to write down my transformation rules here. So notice that really the mean is the one that has different operations for each depending on which linear transformation we're doing. And the spread is only dependent upon whether or not we are multiplying a constant or not. Because notice once we multiply, these two stay the same. But yeah, these are just our rules for linear transformations of a discrete random variable.